And how do we store them? Like, what is this? This is list of list, right? So you can imagine them in terms of indices. So this is 0th index list, this is 1th index list, and this is 2nd index list. So if someone gave you an information that 1 is connected to 2, and in trees they are connected in bidirectional. What I mean by bidirectional is, if 1 is connected to 2, then 2 is also connected to 1. If I can go from 1 to 2, then I can also go from 2 to 1. So it's kind of bidirectional. So what we do is, let's say someone gave you a node 1 and 2, says that 1 is connected to 2. So what we do is, we create a list of lists, something like this, and 1 is connected to 2. We say that. So we go to the 1th index list and push there 2. Basically insert element 2. This means that 1 is connected to 2. At the same time, we go to the 2nd index list and put there 1, saying that 2 is also connected to 1. So 2th index list is this one. So we insert 1 over here. And if I have to write the adjacency list for this tree, this will look something like this. Imagine this is list of list, and this is 0th index, 1th index, 2th index, 3rd index, 4th index, 5th index, and this is 6th index. So this is 0th index list, 1th index, 2th, 3rd, 4th, 5th, and 6th. So 1 is connected to 2. So we go to the 1th index list and insert there 2. And same we need to do also for the second node. Since 1 is connected to, then 2 is also connected to 1. In trees, they are bidirectional. I have already discussed that. So we go to the 2th index list and insert there 1. And same goes for here. Go to the 1th index, insert 3. Go to 3rd index, insert 1. Since 3 is also connected to 1. And same, go to 3rd index, insert 4. So this is 3rd index, insert 4, insert 5, and then insert 6. Also go to the 4th index, insert 3. Go to the 5th index, insert 3. Go to 6th index and insert 3. Right. This is how the adjacency list will look like. And now that we have stored the elements, like how the adjacency adjacency list is created, and this is how we will insert the element. And now, how do we know that which elements is connected to how many other nodes? If someone now, let's say you know how to store these, right? And someone says that what are the childrens of node 1? So what we do, we go to the indexes of list number 1, and whatever the elements are present inside that, we can for sure say that those are the childrens of 1. If you do not know what are the childrens, if I'm talking about node 3, then node 1, node 4, node 5, and node 6 are the children of node 3. If I am particularly talking about a node 3. Same for node 6. What are the children of node 6? 3. And 3 is the only element that is connected to 6. So 3 is the children of 6. As well as there is another concept of called as parent. So if I have to consider this node, what is the parent of node 2? This is 1, right? And we assume that this is the root of our tree. Then root element does not have any parent. So parent of the root element is always -1. You can assume anything as you like, but the parent of root element does not exist. And same here, what is the parent of node 3? It's 1. What is the parent of node 6? It's 3. What is the parent of node 5? It's 3. And same for the node 4. When I'm saying node 4, you can assume it to be a vertex as well. Uh, Somewhere it called vertex, node, whatever you want to call it. And these are all called as edges in a tree. These all are considered as the edges of the tree, and these all are considered to be the vertex or node of a tree. And let's also learn about one few things. What are the leaf nodes? And also talk about the root node. So let's say, so we consider a root node who does not have any parent, right? So in some particular tree, you can consider 3 as the root node. In some particular tree, you can consider 1 as the root node. It does not matter to which root node you are rooting. just the elements ordering changes. If I assume here the root node is 1, then this will not have any parent. And we call a node a leaf node if if it has exactly one children and it is not a root node. I repeat, we call some node a leaf node if it has exactly one children and it is not a root node. So for example, look at this node 2. This has exactly one children connected to 1, and this is not a root node. So this is considered to be a leaf node. Can we consider the leaf node 3? It is not, because this guy is having 3 children, 1, 5, and 4. Assume node number 4. This guy has exactly one children, and this is not a root node. So we call this as a leaf node. And same for the node 5. This is also a leaf node. This is the another terminology of this root. And there are few other terms related to this tree, what are the ancestor, predecessors, and many more. But as we go forward, we will look into those terminologies. For now, we will see some basic properties related to this tree. So if a tree has n nodes, then there will be exactly n minus 1 edges. I repeat, if a tree has n nodes, then that tree will have exactly n minus 1 edges. You can write in your copy, draw some tree, and you will see that if there has n nodes, then there will be exactly n minus 1 edges. If there is not having n minus 1 edges, then that is not a tree. I repeat, a tree is something which has n nodes and does not have any cycles. And we do not count a self loop, like a node 1 is also connected to node 1. We do not consider this, right? So if it has n nodes, then there will be exactly n minus 1 edges, and the tree will not be having any cycles. What I mean by cycle is, you can consider something like this. See this graph. Actually, this graph is a cycles in there, right? You can go from 1 to 3, you can go from 3 to 4, you can go from 4 to 1 again. So there is a cycle of something like this, or you can also see something like this. This is not possible in trees. You will have a single unique path from any u to v. What I mean by that is, if you consider any path, basically any two nodes u and v, then there is only one way you can reach from node u to node v. And if you are saying that there is a cycle in a tree, then you are violating this rule. And also there does not exist cycles in a tree. So these were the few terminologies related to trees, and as we go forward, we will see some more. For now, we have learned how to store the data, like creating the adjacency list, and then depending upon the u and v, go to that indexes list and insert v, as well as go to that indexes v and insert u. Now that we have learned how to store these data, how do we actually traverse in this tree? This is a tree, and if you want to simply like print any order, like there is some order or there are some traversal techniques, how do we do it? Like how do we traverse in the adjacency list and compute the result? Let's say, for example, this one. Let's say we have some tree 1, 2, 3, 4, 5. There are many traversal techniques are there: pre-order, in-order, level order, BFS, DFS, and many more. But particularly to solve the problem, today we'll be discussing only the DFS algorithm, and that is our goal for today, since we will be solving problem related to diameter of a tree and subtree and all. What is DFS? It's nothing but the full name of this is depth first search. We first go to the depth, and then go to the another depth, and then the another depth, and so on and so forth. This is nothing but a traversal technique that we do in a tree, and you can assume that how we do a linear traversal or a binary search traversal technique in our linear array. And over here we have a DFS. This is also a traversal technique that we apply on a tree itself. And what DFS function does is, you provide him some node, and it will start the DFS traversal from that particular node. and keep on going to the def and do its job. And in between that, whatever you want to compute, you can compute it. So let's say node 1, if I start a DFS traversal from node 1, what will happen is it will go to the node 1 first, and then node 2 like it can also go to node 3 as well as node 2. So depending upon how the adjacency list are stored, the elements will be printed. There is no unique result of a DFS traversal. If this is a one after one, there you can print 2 as well as you can print 3 if you are starting a DFS from node 1. So let's assume that from 1 it went to 2, and then from 2 it has nowhere to go, so it will go back. And from node 1 we have already visited node 1, also it cannot go to node 2 since we have already visited that node. So it will have it has only one option to go, and that is node 3, since node 3 is connected by node 1. And same for node 3 here. Node 3 has two choices, either to go 4 and 5, and depending upon how the elements are stored in the adjacency list, it will go by its own. So let's say it went to 4, and again from 4 it has nowhere to go, so it will go back. And again 3 has one element left to go by, and that is 5, so it will go to 5. And again for 5 it has nowhere to go, so it will go back. And eventually for node 3 there is no one left to be traversed, so it will go back. And eventually for node 1 there is no one left uh, to be searched for, and then finally our DFS traversal is over. So if I want to really print this traversal, how the elements were accessed, in what time elements were accessed, so it will be something like 1. I'm assuming that I have started DFS traversal from the node 1, so it will be node 1 and 2 or 3, 2 3, let's say 2 and 3 and then 4 and then 5, something like this. And this is how the DFS traversal works. So now let's see how do we implement this in code itself. How do we implement it? Anyone has any idea? How do we implement this in the code? Or just say what logic we should apply to solve this. There might be some technique to. Yeah.
Recursion.
Yeah, exactly. We can see that how the recursion works here, going to one node and then going to another node from that node, and then keep on going until and unless that node has nowhere to go, it will go backtrack. And that is where the concept of a recursion comes in. So and that is the reason we can see a recursion going on over here. And in between that, what we can do is we can print our elements, and we can see that which element were printed at what time and so on. So we will use the concept of recursion over here, and we will see the implementation of how we implement this. Assume we have an adjacency list, stored the information about how the trees are connected to itself. I can have you must be having information from node 1, where can you go. In adjacency list number 0th index or 1th index, will have information about what are the nodes connected to 1, right? That is what adjacency list does. If you go to the 4th index list, and all the elements present in the 4th index list, those will be the children of that node. And we will go to each and every node present in that node until and unless that node has already visited, right? This is what we will be doing in DFS traversal. And what we do is we have these adjacency list, and we have a visited array as well. There is another implementation, like if you do not consider a visited array, a single parent variable can do the job. But for the simplicity, I will be considering the visited array for this DFS traversal. If you want it, I can show you how a single variable can do it without considering this visited array. So imagine we have 5 nodes over here. So obviously we will be creating a visited array of size 5 at least. 0, 1, 2, 3, 4, 5. And initially they all will be marked with 0. 0 signifies here that initially no any nodes are visited. So we can start the DFS traversal from anywhere you like. So let's assume we have started our DFS traversal from node 1. Can we print this element? Obviously, we can print this element since that element is not visited, right? Initially, all are zeros. Zero signifies they are not visited till now. So if I start the DFS traversal from node 1, okay, go ahead and print it. I mark that node as a visited. So this node has already been visited. And what is the next step that we do is we ask the current node, what are the children's of you, what are the nodes that you are having? Basically, what are your children's? So one says I have 2 and 3. So what we say is, okay, go to anyone anywhere else if it is not visited. I repeat, if it is not visited, go to that node. So one says, okay, I can go to 3 as well as I can go to 2. So let's say he went to 3. Let's say he went to 2 and says that 2 is see that 2 is not visited. So what we do is we print the 2 and mark it as visited. And again we go to the node 2 and ask the same thing. What are your children's? So 2 says I have only one children, which is a node 1. So we first check, is it visited? Yes, it is already visited. So we do nothing. Since the node 1 has already been visited, we do nothing and we go back. So we came here, we went back, and then one one already had said that okay, 2's job has already been done. So I will go to node 3. And we ask the same thing for node 3. Have you been already visited? So node 3 says that no, I have not been visited. So just print it and mark it as visited. And we ask the same thing for the node 3. And he says, I have a children called 4. So we went there and asked the same thing. Are you visited? So this guy said, no, I am not. So just mark it as visited and print it. And again, 4 has one children, that is 3. But 3 is already been visited. So 4 will do nothing and go back. Again, for node 3, one left job is to go to node 5. So go to node 5 and check if it is already visited or not. No, it is not visited. So we'll mark it as visited and we print it. And since 5 has only one place to go, that is 3. But since 3 is already visited, we do nothing and go back. And for node 3, there is one still left node to go by, that is node 1, but that is also visited. So we go back. And ultimately, node 1 has visited all its children, including himself. So we will go back. And this is how the traversal will be done and the elements will be printed. If I have to implement this, should I implement this or can you implement it by your own? Let's just say this is what the first section. I will implement it for you. There is two things to keep track here is the adjacency list, how we create the adjacency list and maintain the visited array, and some vector to store this result like 1, 2, 3, 4, 5. Let's see how we do this in code.
Raj, you can just show the code. You need not implement it now. It will take too much time.
sudo का टाइप लिख
You
देता
can.
हूँ. अच्छा कोड wait, wait, wait. इसका आर्टिकल पसंद नहीं आएगा मेरे को. Wait, wait.
Linux Mint? What the?
Okay, you can see the DFS implementation here. How do we create the adjacency list? You can forget the m number of edges over here. You can do it something like n and then n, and we know that there will be exactly n minus 1 edges. So what you can do is you can iterate through exactly n minus 1 edges, and we take the two nodes u and v. We take the input and go to the uth index list and insert that element that is connected to u, that is v, as well as go to the vth index list and insert the node u. And this is how the adjacency list is being created. And this is the visited array that I was talking about. Initially, we take of size n+1. We marked everything as 0, mentioning everything is non-visited for now. And then we take this resultant array to store the elements, how the order will be, how the order of elements will be. And then we take input for the source node from where you want to start the DFS traversal. The example that we took, we started the DFS traversal from node 1, right? You can start from anywhere as your wish. The result will be changed depending upon what you need. You can start the DFS traversal from anywhere as you like. And then we run the DFS from the source node and provide the input for the visited array, adjacency list, and the resultant array. You can do one thing. You can do this as a you can declare this adjacency list globally, but since I'm not a big fan of this declaring this as a global, you can see that what you can do, DFS traversal visited array, and don't forget to pass it by a reference, since we are going to change this visited array time to time, and there is no need to pass it by reference for the adjacency list, since we will not be changing anything in particular to this adjacency list. As well as you need to pass it by a reference to the resultant array, which will be storing our DFS order. And then initially what we do is, whatever node you are going at, we insert that element to our list and then mark it as visited. And then what we do, we go to all its children, for each and every children in adjacency of u. What this is saying is, for each and every children here is v connected to node u, you go there, and if it is not visited, do the DFS from there. So what this is saying is, if I'm at node 1, what we do, we insert that element in our resultant array, we mark it as visited, and for each and every v here is 2, 3, and what we say is, if 2 is not visited, go there and do the same thing what we were doing, that is DFS from here onwards. And if the job of this node is done, then go back, and same goes to 3. And then if the job start doing insert this element, mark it as visited, and if do the same job from this node onwards. So that is what this one is doing. If it is not visited, do the same job that we were doing from doing previously by passing this node. This node is v, mark same visited, same adjacency list, and same resultant. So this is where you can see the recursive call that were being made. If it is not visited, do the DFS traversal from that nodes only. If you have any problem understanding this DFS algorithm, you can go message here. Anyone having any doubt, you can raise your hand and ask me if you are still not getting the DFS algorithm.
Bhaiya, can you re-explain the recursion part?
Okay, so see this tree, what is happening. Let me see. So imagine we were at node 3, right? What we can do, the first thing we do is, see the code. The first thing we do is put that element into our resultant array. So we printed 3, basically printing or inserting that element into a resultant array and mark it as visited. Think in this way, why we came to this node? Because it was not visited, right? And that is the reason we came to this node. So we mark it as visited, and what we say, for each and every children of this node 3, what are the children of node 3? Go to adjacency of u. U currently is 3. So ADJ of u, what will say that, go to the adjacency list of index u, index 3, and what are the elements present in this index? So it will be 1, 4, and 5. Will it go to node 1? No. See this code. For each and every v in ADJ of u, for each and every children of 3, that is 1, 4, and 5, go there if it is not visited. So from here, if it tries to go to node 1, You cannot go there since it has already been visited in future. How you came here? By node 1 only, right? But can we go to here? Yes, obviously we can go there since this is an unvisited node. So we go there and start the DFS traversal from this node, this V, if it is not visited. And when in the second step this went to the DFS traversal, it will again, what it will do is go to node U, basically insert this element into a resultant array, that is 4. And then for each and every children of this node 4 again, what are the children? It's 3. But since 3 is already visited, this guy has no any other works to be done. So you go back, right? This recursion call is over. So you go back. When you go back, 3 has one more job left to be done. That is to go to the node 5. So you go to node 5, mark it as visited, insert that element into your resultant array, and then tries to solve the job that has to be done by node 5. The only way he can go is node 3. But since that is visited, he has no any work to be left to be done. So he go back. Again, all the job of node 3 is done. So he go back. So this is how recursion is going on over here. You go to some particular node, and if it is unvisited, insert that and do the same job, that is doing a DFS traversal over here from that particular node only. Now you got it?
Yes, भैया.
Good. और किसी को कोई प्रॉब्लम है क्या इम्प्लीमेंटेशन में या इम्प्लीमेंटेशन समझने हैं? If not, then we will be discussing one problem that is so famous called as the diameter of a tree. Okay. So now the questions related to tree will get started, and we see the very first problem for today. This is node 2, this is node 3, 4, 5. So how many of you have heard the term diameter? Not the circle diameter, but the diameter of a tree. How many of you had already heard this term, diameter of a tree? If not, let me define it for you. The diameter of a tree is the length of the longest path from any node U to V present in the tree. The length of the longest path from any node U and V. So if I consider this node and this node, let's say U is 4 and V is 5, the total length you can do is 1 this edge and another this edge. So length is 2. But is it the maximum one? I don't think so. So let's say we take another U and V. Let's say this is my node U and this is my node V. Sorry. U equals 1, V equals 5. What is the length? It's again 2, right? Can we make it better? Obviously. Imagine this node U equals to 2 and V equals to 5, and try to travel from node U to V. And as I have already said you guys, there is only a single unique path from any node U to V. So go ahead and travel from node U to that node V. So if you travel away, the number of edges that you meet is 1, 2, and 3. And this is the maximum possible that we can do for this particular tree. And this is what we call it as a diameter of a tree. The length of the longest path of any node U and V present in a tree. You cannot say node 50 and 5 since 50 is not present here. And how do we compute it? Anyone have any idea? Given a tree with n nodes and -1 edges, find the diameter of a tree. And given the definition, diameter of a tree is length of the longest path from any node U and V. Anyone? Any suggestions? How do we compute this thing? If no,
Number of edges, the global minimum and global maximum.
sorry.
I mean, number of edges between the minimum number and the maximum number.
No. You mean to say is the number of edges between node 1 and node 5.
No, node 2 and node 5.
Node 2. Let's say I change this to node 1 and node, let's say this is 2 and this is 5. Then the result is same. But the nodes can be anywhere, right? It does not matter. 2 can be present here. Any other idea? Anyone? If not, let's see how this is being implemented. There is a term called as depth of a tree. How many of you know this? The depth of a tree. So let me tell you what is a depth of a tree. Imagine this tree only, which is 1, 2, 3, 4, and 5. If I have to define a depth array for this, basically to define what is the depth of a particular element in that particular tree. So for this tree, if I'm assuming my root node is 1, remember here, I am assuming root node to be 1. If I assume some other nodes to be a root, the answer for the depth of a particular node changes. So for an example, I consider root node to be 1, the depth of this root node will always be 0. And on the second hand, what is the depth of this node 1? Node 2? It's nothing but 1 plus the depth of its parent. Who is his parents? Node 1. What is its depth? 0. So 1 plus 0 is 1. So depth of these 2 is 1. Same for node 3. What will be the depth? 1 plus depth of his parent, which is 0. So this will be 1 again. And what will be the depth of node 4? It will be 1 plus the depth of his parent, which is 1. So this will be 2. Same for this one. 1 plus 1 will be 2. And how this will help in determining the diameter of a tree? Assume this one. What will a diameter of a tree will have? It will have 2 nodes, right? U and V. So if somehow we can find what are these 2 nodes, U and V, I think we are done to solve this problem. If we can somehow find these 2 nodes, basically 2 endpoints of the diameter, in this previous example, it was 2 and 5. 2 and 4 can also be another solution, but assume 2 and 5 are the nodes we found, then we can find the diameter of a tree, right? And if you see the structure of the tree carefully, you will see that the node 2 and 5 will have some property related to him. What I mean to say is, if someone tries to be the 2 endpoints of a diameter, he must be having some property, right? And this is where the depth of these elements will help us. How? Let me tell you. So imagine you are given a tree and you start the DFS traversal and compute the depth of each and every element. No matter from where you start, it's totally fine. What we are going to find is what is the deepest node if I start a DFS traversal from that node. For an example here, wait a second. For an example here, if I started a DFS traversal from here and computed the depth for each element, I found out that 5 and 4 are the 2 elements which is the deepest node, right? Since they both are having 2 as the depth, and 2 is the maximum depth that an element is having in this tree. Depth of this is 1, depth of this is 1, and depth of this is 0, and depth of this is 2 and 2. Can I surely say that I can consider any one of these elements as one endpoint of my diameter? Yes, we can say that. What I said, let me recap. You start a DFS traversal from any particular node. It does not matter. We are only concerned about finding the deepest node from any node, from DFS traversal from any node as you like. And then what we do is, from that node, what you have found right now, we do a DFS traversal again from that node and compute the depth again, and then find the deepest node from that found node. So what I mean to say is, let's say we started a DFS traversal from node 1, we computed the depth for each and every element, and we found out that 5 and 4 are the elements who is having maximum depth, right? So let's say I consider 5 to be one end of my diameter. So what I do is, I again start the DFS traversal from this node, that is node 5. You can also start from node 4, it does not matter, since we are only concerned about finding the length of the diameter, not the elements of the two ends of a diameter. So you can start it from any point, it does not matter. So let's say I started a DFS traversal from this node, and again we do the same stuff, that is finding a deepest node from this particular node. So if I recompute the depth, what will be the depth of this element? This is 0. And what will be the depth of this element, which is 1? And again, what will be the depth of this node 4? This is going to be 2. If you are not visualizing it, what I'm saying is, let's route the tree now to node 5. So if you route the tree to node 5, the tree will look something like 5, 3, and from 3 it's connected to 4, from 3 it's connected to 1, and from 1 it's connected to 2, right? And what I'm saying is, you start the DFS traversal again from here, and we compute the depth again. So depth of this is 0, this will be 1, this will be 2, this will be 2, and this will be 3. And in the second attempt, whatever the maximum depth we got, that will be our final answer. How many of you agree with me? I think this is the correct way of implementing the diameter of a tree. Obviously, there are many other implementation to be done, but this is how I do it to find the diameter of a tree. Let me recap it for you. We do a DFS traversal and maintain a depth array and do a DFS traversal from any given node, any particular node you can start. You can start from node 1, 3, 4, and 5, and make sure that particular node is present in that tree, right? So if total node is 5, you cannot do a DFS traversal from node 50. That will not get you to somewhere near about result. So you can start a DFS traversal from node 2, node 3, node 4, node 5. It's up to you. And then compute the depth of this entire element. And then you find the deepest node. If there are multiple such nodes, then you can consider any one. And from that considered node, you again do the DFS and again compute the depth. And next time when you compute the depth, whatever the maximum depth you got for any particular node, that will be our final answer. I hope you got the idea. And how do we compute the depth here? Doing a DFS traversal. If you remember, our DFS traversal was looking something like this. For each and every children in adjacency of U, sorry, if not visited of V, then we do DFS from that vertex V, right? And we add one extra step, that is we will be having a depth array, and we save that depth of this node, this children, is nothing but 1 plus the net depth of this parent. So his parent is node U, right? So what this will do is, assume you are at this node 3, and you want to go to node 4 and want to go to node 5. So node 4 depth will be something like 1 plus what is the depth of my parent. So his parent is 3, that is U currently, and his depth has already been computed. So it will give him 1, and we add them up, and we get 2. And this is how we fill the depth array here. Is there anything that you can ask if you don't get it, like how we compute the depth array? Anyone have any issue? Yes, no? मैं कंफ्यूज हो गए. समझ आ गया ना कैसे कंप्यूट होगा?
If anyone has any issue, you guys can raise your hand. Like, we are here to clear your doubts.
Even if you are getting the story, it's totally okay. Don't get into coding scheme right now. Just you can visualize the story what we are doing here. Randomly pick a node, do a DFS traversal, fill the depth array, find the maximum uh, node having maximum depth, and from that node again do a DFS traversal and again fill the depth array and find the maximum depth you got, and that will be the diameter of a tree. The idea is pretty simple, and there is a question to be done. There is pretty similar question, CSES questions out there. So you'll be given a tree with n nodes, and when they say that there is n nodes, there will be exactly n minus 1 edges. So if you see the example test case here, so they are having node 5, number of nodes is 5, and there will be 4 lines of input, right? One is connected to 2 as well as 2 is connected to 1. They are bidirectional. And then 1 is connected to 3, and then 3 is connected to 4, and then 3 is connected to 5. If I draw this, will look something like this. 1 is connected to 2, and then 1 is connected to 3, and then 3 is connected to 4, and then 3 is connected to 5. And why the diameter of a tree is 3? Because you can pick this node U, and you can pick this node V, and if you walk along this path, you see that there are 3 edges that will meet, 1, 2, and 3, and this is the reason why the output is 3. I hope you can code this up right. If you want to see the implementation, I have just coded it here, I can show you. Okay, you create the adjacency list. We have already discussed it. You keep a depth array, and we for now we say that we have a maximum depth of -1, and the current node is -1, and we do a DFS traversal from one node 1, and we assign the parent to be -1, and we pass the adjacency list and the depth array to be filled. And what this DFS algorithm will do? Simple, it's U and the parent of U and the adjacency list and the depth array. For each and every children, if it is equals to parent, same as the visited array. For now, if you are confused, not getting this child and parent, you can maintain the visited array. That is also totally okay. And we compute the depth of this child. Basically, depth of this V is nothing but depth of U, which is the current node, plus 1. And then from that node, you will start the DFS traversal again. And in the next step, what we are doing is we are checking that what is the maximum depth, and at the same time we are updating the node. So if there is some depth of node, let's say 2 is having a depth of 1, so we will say that for now our answer is node 2. Again in future, let's say node 5 is having a depth of 3, so we update our node to be 5. And again we are also assigning a depth of I to be 0. Why? Because we need to compute it again, right? From whatever node we get it from here, the maximum deepest node. And when we will be getting a node having the maximum depth, and from that node we will again start the DFS traversal, assigning the parent of this to be -1. Why? Because now we have assumed that this node is the root of my node. And again the same adjacency list and the depth array. Remember, we have already reassigned the depth of I to be 0. Refill this to 0, and then again from there find the maximum depth, depth of I, calling the DFS, and then you can output the max depth. And this will be the implementation for the diameter of a tree. If you know how to implement the diameter of a tree, I have one more question related to the diameter of a tree only. And for in this question, you need to apply some logic based on what we have learned till now, the diameter of a tree. In this problem, you are given two trees, right? You will be given two trees of different node size. One can have 5 nodes, one can have 6 nodes, and you will be given the information about the edges as well. And what this is saying is, this problem is asking you basically, if you want to read this out, you can read it out for now, and then read the constraints as well. Those are very important. Okay, I hope you are done with reading this statement. So this problem is asking you will be given two trees. Assume this one. 1, 2, 3, 4, 5, and 6. And you will be given another tree. 1, 2, 3, 4, and 5. And what they are saying you to do is add one edge, add exactly one edge between these two trees such that the overall diameter of this tree will be minimized as mean as possible. So let's say this two tree were given as an input. What you can do, you can say that I will connect this node to this node, but you are not checking the second condition, that whatever node you are connecting to, check the overall diameter of a tree. What will be the overall diameter of a tree? See this edge 1, 2, 3, 4, 5, 6, 7, 8. If you connect an edge from node 5 from one tree and node 2 to another tree, the overall diameter will be 1, 2, 3, 4, 5, 6, 7, 8. The overall diameter will be 8, right? But can we do this in lesser? Can we do this? Let's say you connect an edge going from here to here. Then what will be the diameter? 1, 2, 3, 4, 5, 6, 7. This is 7, right? So you see the difference. You cannot just randomly connect any node to any node to any node, since that may not give you the minimum diameter possible for the entire tree. So you need to find a way such that you can say that, okay, I will be connecting this node to that node, and that will give me the minimum possible diameter of the overall tree. What is the logic that you can develop here? Anyone? What will be the efficient way to connect this node? Or is it necessary to even connect the node? Can we find the answer knowing just the diameter of this tree? Obviously, the question is about diameter of a tree. We can do some observation here and can potentially find what will be the minimum possible diameter of the overall tree. Can anyone? Assume that, let's say, you know the diameter of this tree to be D2, and assume that the diameter of this tree to be D1. Can we find the minimum possible diameter that you can construct? Can we find it? How can we find it? Okay, let me give you a hint. We actually even don't need to add an edge between any node to any node. We don't need to take care of that. If we know what is the diameter of a tree first and what is the diameter of a second tree, then we can compute what will be the minimum possible answer. How can we find it?
भैया D1 plus D2 by 2.
Not exactly, but good guess. Why do you think that will be D1 plus D2 by 2?
भैया first tree will take half the depth, we will calculate it from there, and D2 half depth will be from there, and we will get the minimum.
Okay, so there could be one better way of saying it, like D1 plus D2 divided by 2. And by the way, you forgot this new S that we have added. So let's say
Yes,
we
भैया
have
plus 1.
still this will not be exactly correct, but you are nearly there. Anyone? So let's see what is happening in the diameter of a tree, right? And so let's say we have a tree with something like this. And for now, forget about what is the tree present over here. And since we need to minimize the overall diameter of a tree, what is the best way? What is the best place? It could be to place an edge in this tree only. Let's analyze this. So let's assume you connected an edge to this node. Then someone coming from here can go to this node, this node, this node, and this node. What will be the total amount? It will be 1, 2, 3, and 4, right? So node, if you connect an edge going from node 1, it will give you a cost of 4, right? Let's choose this node, and we have connected to some node to this tree. Forget it about now. And someone can come from this node, and what will be the total cost? And by the way, this edge is not there. Then that guy can come to this node and count it as 1. Then he has two options to go by. Either he can follow this path or go this. And by the definition of the diameter, we already know that it should be the length of the longest path. So it will follow this path, and the total will be 1, 2, and 3. So for this node, the cost is 3, right? Assume this node. What will be the cost? Someone coming from this tree, he can reach to you. And since we know the definition of the diameter, which is the length of the longest path, it will not follow this path. It will follow this path, which is 1, 2, 3. So again, answer for this node is 3, right? Again, for this node, if you connect something to this node, the cost will be 1, 2, 3, and 4, same as the node 1. What did we see? We see that the best place to do it is the middle of the element that the diameter of the tree one was. What I mean to say is, if I assume the diameter of this tree D1 to be D1, then no matter where you place the edge, the answer is D1 divided by 2. This will be for sure, no matter what. This was 4, from there it will be 2, and this will be 2, and this will be 1, 2, 3. So minimalist you can make is node 2, basically 2. And how can we say that? It's d by 2, right? What was the diameter of this tree? 1, 2, 3. So 3 divided by 2 is 1. This is minimalist possible. Sorry, the diameter of this is the diameter of this tree is now even, and we say that d1 divided by 2 will be as like there. You will have to include this to our answer, that is d1 by 2. You cannot make a minimum minimalist than this. And now let me show you one more example. Assume there is a tree having an even length of a diameter, and there is another tree with odd length of a diameter. What do we think the best place will be? What is the minimalist possible that you can make to this tree and you can make to this tree? If you add this to this node, then he can follow this path, and you will have at least two edges to go by. And but in even case, you will exactly have, if you place an edge from edge to this node, he will have 2 on this side and 2 on this side. So for the even length diameter, the answer is d1 by 2. But for the odd one, it's d1 by 2 plus extra 1. Because if you add this node, he will follow that path. If you add to here, he will follow this path. So there is always plus extra 1 that the odd length diameter will have. And the overall formula that will come to compute this is, as we have already discussed, d1 divided by 2, we have to add this one. Also d2 divided by 2, we have to add this one, plus 1, the extra edge that we are adding, right, to connect the both of the tree. And if the diameter of the first tree is odd, then we have to add extra 1. Assume this is our some result. And also we check that if the diameter of the second tree is also odd, then we have to add extra one. And the final result will be d1 divided by 2 plus d2 divided by 2 plus 1. This plus 1 is the new edge that we are adding to join these two trees according to the statement. And if the diameter of the node diameter of the first tree is odd, we have to increment this. And if the diameter of this tree second tree is odd, we have to again increment this by 1. Still, if you are not getting it, let me, like, till now have you understood it or not? Why this d1 mod 2 equals to 1, then we can add resultant. You can see this one, right? Let's assume 3 and 4. 1 2 3. Okay, so that diameter for this tree is 3, right? And this is odd. The best we can make is d1 divided by 2 plus 1. If you add an edge to there, this will be 2. If you add an edge to here, it will be 2. If you add to here, it will be 3. This is even worse. So how we got 2? So it's 3 by 2 plus 1. That is 1 plus 1. This is 2. But in case of odd elements, basically odd length of a diameter, see this one. The best place is always the middle element. You go by this 1 and this 1. How we got it? The diameter is 2 divided by 2, which is 1. And since the diameter is even, we don't need to add extra 1 as we are doing over here in case of odd length diameter. This is what we can do to solve this problem. Anyone have any doubt? Do let me know. Anyone? If not, I can show you the code. Okay, this is Java. Sorry. You create the diameter. Sorry, adjacency list. You compute the diameter for first tree. We have already discussed how we compute the diameter. The same stuff is going on over here. We write the DFS function, do the pretty same stuff that we have already talked about, finding the diameter of a tree. And then let's say this is our resultant vector. So d1 divided by 2, we have to add this amount, and d2 divided by 2, we have to add n plus 1 for the new edge. And if the diameter is odd, it will be incremented by 1. If the diameter is d2 is odd, we have to increment it by 1. And we have to maximize it with both the diameter. Let's say we computed the diameter d1 divided by 2 and it is lesser than both whatever the initial diameter of d1 and d2 we're having, then that is our wrong answer, right? So we also need to maximize it with d1 and d2. And this will be the code for this problem. You can solve this. I will provide the link for this problem. Now did you get the idea for the diameter of a tree or not? What is the diameter of a tree? हाँ ना, कुछ तो बोलो. कुछ कुछ है, समझ नहीं आया या समझ आया? ओके, गुड. बाकी सब कहाँ है? Abhishek Mishra, are you there?
Yes, dear.
What is the definition of a diameter?
The diameter is the longest path between any two nodes.
हाँ, good. Okay then. Moving forward, these subordinates. Okay. So now we will be getting into a deeper application of a DFS algorithm. Wait a second. So now we will see the deeper applications of the DFS algorithm, and there is a beautiful question to understand it. Uh, Another question is, you will be given a tree and what you need to compute is the subtree sizes for each and every node. Let me define a subtree for you. You can see, you can assume this node 2 to be a subtree itself. You can say this to be a subtree itself. Also, you can say the entire tree is a subtree as well. I hope you got the idea for the subtree. If I have to define it in another way, this entire thing is one subtree of this entire tree. Also, this 4 is a subtree of size 1 of this entire tree. So this is what the subtree is. So if someone is asking you, find the subtree sizes for each and every node, given that the root node is 1, compute the subtree size array for me. And if I have to talk about what will be the subtree sizes for this node, root node 1, it's 1, 2, 3, and 4, right? How many elements are present beneath this node? It's 1, 2, and 3, and 4. So the answer for this should be output as 4. And for this node 3, there are two guys who is beneath this node 3, basically connected in subtree of 3. So this will be 2, this will be 0, and this will be 0, as well as this will be 0, right? And what we see here is leaf node will always be having the subtree sizes as 0, since there is no any guy present beneath that node. And as you see this node 3, how he will get the answer as 2, and see this node root node 1, how he have got the answer as 4. He can get the answer as 4 if he knows all the information about all the answers about its children. Like, if I can get the answer from this node, how many guys you are having? If he can get the information from this node, how many guys you are having, then this guy in root 1 can add all these results and say that this is my answer, right? So let's say this subtree rooted at node 3, what will be its answer? And we already know the answer for this will be 0, the answer for this will be 0, the answer for this will be 0. And whenever we are going back, we say that you take 1 and also you take 1, and what will be the answer for 3? The answer will be addition of these two guys, which is 2. And again, when going back, this guy will say that I was having answer of 2, but take extra 1. Why extra 1? Because I am connected to you. So this will, same thing was happened over here. The answer for this guy will having 0, but he will send answer as 1, since this guy won't get counted for this node. And this guy will send node 3, since the number of nodes here will be 1, 2, 3, and this guy will send 1 to him, and if we add them up, this will be 4. And again, if the information was supposed to be passed by this node, it should be 5. But this guy only needs to the result, so he will add them up, that is 3 plus 1, and the answer will be 4. We will see how the DFS algorithm will compute this. For now, if anyone is having any idea how to solve this, you can mention it. Anyone? There is another way to explain this to you. What you can do is, you can assume the subtree sizes for the leaf node to be 1. that will make our life easier. And then when we are displaying the output, we will subtract it by 1. What I mean to say is, whenever we do a DFS traversal, we will come to this node and say that, hey, you are a leaf node. You will not be having any job to do. So I will assign a value, or basically answer for this node to be 1 and go back. And this node 3 will go, it will go to 4. And again 4 will say, I do not have any other job to be done. So my answer is 1, and this guy will go back. And again 3 will go to 5, and then 5 will go to 6, and then again 6 will say that, okay, I will be 1, and as well as 7 will say that I will be 1. And then when we go back from here, what will be the answer of 5? It will be the summation of all these guys that were returning to him, that is 1 plus 1, that is 2. This will be the answer. We will add extra 1 to this guy. So basically, we have an answer array 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, and 7. So initially all are zeros. We go to node 2 and we found out that answer will be 1. We go to node 4, we found out that answer will be 1. And we go to node 6, the answer will be 1. And 7, the answer will be 1. And again for node 3, node 5, the answer will be the summation of all its children plus 1. So it's 1 plus 1 plus 1 for him itself. So the answer is 3. So for 5, the answer is 3. And this will return him 3. So 5 is returning an answer 3 to its parent named as 3. And this guy was returning 1. And if we add them up, it's 3 plus 1, 4. And if we add extra 1, including himself, this will be 5, right? So the answer of this node to be 5. And again here, when he will go back, he will report his answer to be 5. And 2 is also reporting his answer to be 1. And if we add them up, it will be 6 plus 1 himself. So it will be 7. 1, 2, 3, 4, 5, 6, 7. As you can see, the answer for this is 7, right? And this is what we need. But according to the CSES problem stated here, they need one lesser element. So by the way, this is not the input example that I have drawn over here. So what we can do is, ultimately you can subtract every one by 1. So this answer will be 6, answer will be 0, 4, 0, 2, 0, and 0. So the answer ultimately for this is 0, this is 0, and we will be able to compute this by subtracting by just 1. You can follow this as well as follow that. Both will work here. I hope you got the idea. And how we do the computation, that is up to you. I will show the code, by the way. You got the idea? If not, the question is stating the similar thing. You will be given a tree and you need to find the subtree size for each and every node. For each and every node, and you need to output the result for node 1, 2, 3, 4, whatever the number of nodes are. So if I have to consider this example, they said that by the way, the input format is a bit different. Let me explain it to you what is going on over here. So there are 5 nodes, and they say that root of basically the manager of this company is node 1, and basically the root node, and they provide with you some number, and this number are something like 1, 1, 2, 3. So this means that this index is 1. So 1 will be connected to 2, and then again 1 will be connected to 3, and again 2 will be connected to 4, the indexing wise. So if I have to draw a tree for this particular example, this will look something like 1 is there, right? So we start with second index. So second is 2 is connected to 1. This is exactly same saying as 1 is connected to 2. And then this is third index. 3 is also connected to 1, and 4 is connected to 2, and 5 is connected to 3. This is how the input is provided. And if you see the answer of 1, that is node 4, we computed it to be 5. 1, 2, 3, 4, and including him 5, if you subtract it by 1, you will get 4, right? And see this node 3, we computed our result to be 2, and if we subtract it by 1, you will get 1, and eventually you see that the answer for 3 is 1, and for 4 and 5, since they are the leaf node, the answer is 0. I hope you got the problem statement. How do we solve this problem? Anyone have any idea? Or just say the approach how to solve this problem. अरे अभी जो पढ़ा वही बता दो एटलीस्ट. इफ्तिकार, you are there?
हाँ भैया.
हाँ, कोई अप्रोच?
भैया इसके लिए डीएफएस ही करेंगे. वो पहले कंप्लीट करके उसके बाद एक बार डीएफएस होने के बाद जो चाइल्ड रिटर्न कर करके आएगा वो पेरेंट में ऐड करके आएंगे.
Yeah, idea is like pretty same. Good. तो ये बिना बताए नहीं बता सकते क्या? पहले नाम बताना ही पड़ेगा. चैट में लिख सकते हो कि क्या अप्रोच होगा.
भैया चैट मिल नहीं रहा.
अरे उधर देखो, पीपुल के बगल में है.
भैया चैट एक्सेस नहीं हो रहा.
ओके, ऐसा है क्या? ठीक है, we will fix this issue by the next session. Anyway, इसके अलावा किसी के पास और कोई ऑप्शन है क्या? ओ हाँ भैया.
कुछ नहीं कर.
अरे ओबीएस चलाना सीखना होगा सही में, बहुत दिक्कत हो रहा है.
कोई नहीं.
एप्लीकेशन ऐसे है बट उसका यूआई क्या है वो. इतना सारा विंडोज है, ये माइक वो माइक, ये वीडियो वो वीडियो, समझ नहीं आता. एनीवे,
और कितना बाकी है?
आई गेस इतना करा के फिर छोड़ देते हैं आज.
या जल्दी रैप अप करो. सही है, तो नेक्स्ट सेशन ले सकते हैं. काफी लेट हो गया.
तो मैं कोड दिखाता हूँ इसका. बेसिकली वही करना है. ये मैंने ग्लोबली कर दिया. And then you create the adjacency list, you call the DFS function, and then we output the result subtracting it by 1, like I have already discussed it. And what do we do? This is for the leaf node that we decide that ADG of u dot size equals to 1 and u not equals to 1. I have already discussed this, right? If some node is having a size of 1 and that is not a root node, that is considered to be a leaf node. And we already know the answer for that node. Subtree of u, subtree here is the answer for the node u or any particular node, which is 1, and then we return from there. And in other cases, we do a simple DFS traversal, whatever the technique was, and you can add this statement to here also, but I generally do this one. I think this is the one I'm getting. And what we do is we go to all its children, and what will be the subtree of size u? It's the summation of all the answer for its children, right? And at the end of the day, we increment the answer by 1. When we are going back, we were incrementing the answer by 1, right? We are incrementing, like saying that, okay, add it by yourself in the answer. And at the end of the day, when we are outputting the result, we subtract it by 1. And this will be the general idea to solve this problem. There could be another implementation to solve this. You can check it out. But this is how I do it. Okay. आज का सेशन में किसी को और कुछ पूछना है क्या? कोई कुछ समझ नहीं आया? एंड हाँ, बाय द वे, ये वाला जो हमने क्वेश्चन किया था, मिनिमाइज द डायमीटर ऑफ अ ट्री, दिस क्वेश्चन हैड ऑलरेडी बीन एग्जिस्टेड इन द कोड फोर्सेस, and few days ago in the lead code contest, it appeared as a D problem, considered as a hard in lead code contest, I think 8 to 9 days ago. There is slight change in the base cases that they have done. You can check it out, and I can show you, right? Wait, the what is it? Let me see the name of this problem. Yeah, sorry sir, thank you. You go to the contest, this 404, and then you go to this one. Yeah, the name of this problem is find the minimum diameter after merging two trees. Right, the statement is same, and they want the same result that we have already discussed. Find the minimum possible diameter after adding an edge between two given trees, and the answer for this is 3. You can do this one as well. There are few edge cases you need to take care in this one. You can do it by yourself. You can check it out. Minimize, what is this, minimum diameter after merging two trees. And there is one still there is one traversal that is left to be done, that is BFS. I think you can do it by your own. BFS is not that tough to be implemented. You can check it out by your own. And I guess, yeah, you made it till here. Yeah, this is good stuff from pre-second year. Nice. And we'll be starting the next session. Not know, we will inform you guys, and we will continue from here onwards only. And we will see the implementation of LCS and other traversal that we do in trees. एंड कर दे क्या भैया?
You can, yeah, recording off कर दो.
अच्छा, मैं तो रिकॉर्डिंग करना ही भूल